Students, this is a fun problem. They're giving us some information about the elements in an unknown compound that contains carbon, hydrogen, nitrogen, and oxygen. And they're telling us about not one but two reactions it underwent and something about the mass of the products formed. In the first reaction they're telling us about, they say it's a normal combustion reaction, and so we can presume the normal combustion format. And then they say, so then they give us mass of CO2 and mass of water. And then they say in another experiment, it is found that 0.103 grams of the unknown produces a certain mass of NH3. We're going to use that second experiment to find the mass of nitrogen. In the first combustion reaction, we'll use it to find the mass of carbon and of hydrogen. And then we can subtract each of the masses that we find from the unknown mass, which they tell us in the original problem was 0.157 grams of the unknown, and we'll get the mass of oxygen. Then, just like the last problem, we'll convert all of those masses into moles, we'll write a provisional formula, and then we'll end up with the empirical formula. Okay, so let's start by writing a combustion reaction for the unknown. Since we don't know its formula, I'm going to use some letters to represent the subscripts. So C, we'll just put a W for its unknown subscript at this point. H, X, N, Y, O, Z. So that's your unknown. As with any combustion reaction, you need to react with a gas that supports combustion, and in almost every case that's oxygen. And we produce CO2 and water. Let's write the masses. They tell us that it was 0.157 grams of the unknown that reacted, and 0.213 grams of carbon dioxide, and 0.0310 grams of water produced. Since carbon dioxide is the only product that contains carbon, and since H2O is the only product that contains hydrogen, we can use mass percent to find the masses of carbon and of hydrogen in each of those. And because of the law of conservation of matter, the mass of carbon in the product should be equal to the mass of carbons in the reactants of this equation. So let's start by saying 0.213 grams of CO2. And we'll multiply by the mass percent of carbon within CO2. If you were to find the molar mass of CO2, you would look up the atomic weights of oxygen and carbon. You would multiply the oxygen atomic weight by 2. So 16 plus another 16 plus 12 gives you 44 grams of CO2 in a mole. And contributing to that 44 was 12 grams of carbon. So to get mass percent, take 12 over 44. So 0.213 grams of CO2 gives us the mass of carbon that's produced. So 0.0581 grams of carbon. Similarly, we'll do a calculation for the hydrogen within water. They tell us you've got 0.031 grams of water. Water's atomic weight, or molar mass, would be found by adding the atomic weights of one oxygen atom and two hydrogens. So 16 plus 1 plus 1. That gives you 18 grams. And hydrogen's contribution to that 18, since there are two atoms of hydrogen within water, is 2 grams. And if you follow the units, you end up with grams of hydrogen for the final answer. And that works out to be 0.00344 grams of hydrogen. Okay, so we've got the grams of hydrogen and the grams of carbon that are found in the products. But what's an extra complicating factor in this problem is that the unknown has 4 elements, not 3. So whereas in question 1 of this WebAssign, you had an unknown that contained just carbon, hydrogen, and oxygen, now you have to deal with carbon, hydrogen, oxygen, and nitrogen. That's where the second experiment comes in. So they tell us, in another experiment, you were doing something with the unknown compound, so CW HXNYOZ plus some other reactants that they don't tell us about. Produced NH3, that's ammonia, plus some other products that they don't tell us about. But you know what? It doesn't matter what those other reactants and those other products are. Because if you look in the parenthetical reference in the problem, they say also assume that all of the nitrogen ends up in NH3 in the second experiment. So that means the only place where nitrogen appears in the product side of that other experiment is in the NH3. So we can use the information they gave us about the mass and figure something about the mass of nitrogen within the unknown. In the problem, they told us that 0.023 grams of NH3 were produced in that second experiment upon the reaction of 0.103 grams of the unknown. That's going to be important, and you'll see in just a second. Okay, so we'll do a similar calculation that we had done before. 0.023 grams of NH3. We'll find the mass percent of nitrogen within NH3. NH3's molar mass would be found by adding nitrogen's atomic weight plus 3 times hydrogen's atomic weight, so 14 plus 1 plus 1 plus 1. The contribution that nitrogen had to that 17 was 14 grams. If you follow the units, you'll get grams of nitrogen in the end. And if you crunch those numbers, you get 0.0189 grams of nitrogen. Now here's the important point. You get 0.0189 grams of nitrogen for every 0.103 grams of the unknown that reacted. But that's different from the experiment that we had worked with before. In the earlier experiment, they had said that it's 0.157 grams of the unknown. So the mass of carbon that we had worked out was the mass for every 0.157 grams of the unknown. And the mass of hydrogen was for every 0.157 grams of the unknown. So in other words, the masses that we've found are not consistent across the board. Thus, we need to do a little converting. Since 2 of our masses are worked out for every 0.157 grams of the unknown, let's convert the only one that isn't. And we'll just set up a proportion. So if we know that you have 0.0189 grams of nitrogen for every 0.103 grams of the unknown compound, we're interested in finding out how many grams of nitrogen we would have for every 0.157 grams of that same unknown compound. Notice the difference here. This is what we had in the second experiment, and that's what we had in the first experiment. So I'm simply going to cross-multiply and solve for the question mark. And it works out to be that you get 0.0288 grams of nitrogen for every 0.157 grams of the unknown. That's a small but very important step going forward, and easy to get tripped up on that. So now we finally have masses that are consistent for each of the elements within the unknown. We know that we've got 0.0288 grams for every 0.157 grams of the unknown. We've got 0.00344 grams of hydrogen and 0.0581 grams of carbon. The only other element that's in the unknown would be the oxygen. So we just subtract. If we have 0.157 grams of our unknown compound, and we know that within that compound we also have 0.0581 grams of just carbon, 0.00344 grams of just hydrogen, and 0.0288 grams of just nitrogen. The only element that we haven't found the mass of yet would be the oxygen, so just subtract to get the mass of the oxygen. And it works out to be 0.066666. Well, I'm going to round it to 0.0667. Finally, we've got to a point where you can start converting grams into moles. So we've got masses for each of the elements in the unknown compound. Let's start with the carbon, 0.0581 grams of carbon. We're going to use the atomic weight of carbon to get moles. If you follow the units, grams of carbon crosses out, and you're left with moles of carbon, and it works out to be 0.00484 moles of carbon. For the hydrogen, it's 0.00344 grams. The atomic weight of hydrogen is just 1, so it's every 1 mole of hydrogen weighs 1 gram. But it's very important to get into moles. Even though that didn't mathematically change your number, it converted from grams into moles. For the nitrogen, 0.0288. And it works out to be 0.00205 moles of nitrogen. I know this problem starts to get long after a while. Part of the challenge of a more difficult problem like this is really just keeping your records straight. You have to be very careful about bookkeeping. Okay, so now we've got moles of each of the 4 elements. Moles of carbon, hydrogen, nitrogen, and oxygen. Next, we're going to write a provisional formula. Using decimals as subscripts, which of course is not proper in format, but we'll fix it in the end. So instead of writing Cw Hx now we can write C, and we had found that the number of moles of carbon was 0.00484. H was 0.00344. N was 0.00205. And O was 0.00417. Next, take the subscripts that you've written in the provisional formula and look for, when you make that division, look for ideally whole number ratios if you find a ratio right near that. But you're not always going to get whole numbers. sometimes you'll get halves, thirds, or fourths. So let's look at the subscripts that we have in this problem. 0.00484, 00344, 00205, and 00417. The smallest is 0.00205. We'll divide all of the subscripts by that. One of them is going to be easy. 0.00205 divided by itself is, of course, 1. The other numbers, well, let's do the easy ones first. 0.00417 divided by 0.00205 is really close to 2. 0.00344 divided by 0.00205 works out to be 1.67, which is 5/3 as an improper fraction. 0.00484 divided by 0.00205 works out to be 2.33, which is 7/3 as an improper fraction. So here we didn't end up with whole number ratios for all of them. A couple of the ratios worked out to be in terms of thirds. So let's neaten that up just a little bit. We'll write 7/3 as the subscript for carbon, 5/3 as the subscript for hydrogen, 1 is the subscript for nitrogen, and 2 is the subscript for oxygen. Notice that the molar ratio of all the elements stays the same, whether you've written it as a decimal or as an improper fraction, or as you neaten up this formula more and more, it's going to look, eventually, you're going to get a whole number ratio in the end. But the ratio is maintained. So if you've got improper fractions in your formula, we do have to neaten that up. Let's triple all of the subscripts. So take 7/3 times 3, because I see the denominator is 3 in those fractions. 5/3 times 3, 1 times 3, and 2 times 3. And you end up with C7, H5, N3O6. And bada bing, bada boom, you have your empirical formula. Easy.